Okay, I'm starting the YouTube streaming. It's all good. Audio is good. Connection is good. Okay. So I will just move it slightly out of your view so that I can keep an eye on it. Because sometimes, when my wireless mic runs out of battery, then from that point on, it becomes a silent movie, which is still useful, because you can still see, what is happening on the screen, but it's not going to be as useful. All right, so let's go ahead and get started. This is what we talked about last time. Okay, do you guys remember the regular expression discussion? Okay, so the regular expression stuff, it's really an exposure more than anything else, which means, if you don't fully understand what is regular expression or cannot understand this entire thing, it's not a big deal, as far as this class is concerned. But what I do want to tell you is it is actually useful in other classes. And if you think that you're gonna get jobs in computer programming and whatnot, regular expression can be very important. Okay, so that's kind of an exposure thing. And then we moved on and talked about how do we convert from a base 10 scientific notation to a double. Okay, so that's kind of where we are at at this point. Okay, so do we have any questions before we move on and continue with this topic? No questions. All right, very good. I also want to emphasize that it's important to attend classes. So missing a class is not a good thing unless there are good reasons. Okay, just because this class does go fairly fast. So missing one class, can cause issues down the line. Okay, and that's also why I'm gonna take row today. So let's go ahead and I have prepared the row sheets many times, but because I'm kind of more eager to talk about the topic of the class, I always forget to actually pass the row sheet out. And I'm not kidding. That really is usually what happens. I have the row sheet ready, and I mean, you guys have taken the P300 from me, and yeah. Sometimes I just forget. It's like, okay, let's talk about your floating point numbers.
Yeah, you didn't do it for like 3 weeks straight.
Yep. Yep.
And they're like, oh yeah, we have a roll sheet.
Yep. Because I keep forgetting. I would bring it and then totally forget to pass it in the class. So. All right, so what we'll do is we'll continue with an example. This is the example that I used yesterday with the other class. We'll start a new one, okay? We'll get rid of this one. And we'll just say, okay, let's say we are talking about 4.56, times 10 to the power of, let's say, 60, okay? So this is in base 10, okay? Now, once again, the syntax of a base 10 scientific notation, we can optionally have a sign here. We can also optionally have a sign over here. The entire exponent part is optional as well. So if you prefer to enter this as 4.56 and then followed by 58 zeros, feel free to do it, okay? But that's the whole purpose or the value of the scientific notation is you can separate the value from the magnitude. Okay, so the value is always just going to be from 1 to about 10, but the magnitude in this case is some powers of 10, okay, which can be like, in this case, it's not even considered really big. I mean, 10 to the power of 60 is something that even an older Casio scientific calculator can handle. Okay, so what we'll do is now we look at this and go like, well, what do we do with this? How do we convert this into a representation in double? So what we want to do, okay, is to rewrite this. Now, do you guys want me to use this to represent x to the power of y, or do you want to use this to mean x to the power of y, or do you want this to mean x to the power of y? I can use any one of the three methods as long as we have an agreement. The second one? Second one is okay? All right, so we'll use the second one. All right. The second one, can potentially cause a confusion because the caret symbol in C and C++ means exclusive OR. Okay, so you will be doing some coding in this class with regard to base conversion and stuff like that. So if anyone shows me the code and they're trying to use the caret symbol to mean to the power of, I'm just going to laugh. Okay, so you have been warned. Okay. All right. So how do we convert this? Well, the first thing we do is we don't okay, remember the whole objective of this conversion, part of it is we do not want to use double math. Okay, we don't want to use the representation of double to convert a number into double. Okay, because that's it's not exactly a chicken and egg thing, because you can't actually do it. But the point is the conversion process, if you use double math, you will encounter two problems. You encounter error issues, and you will also it will also be inefficient on any platform that can only support hardware integer math. Almost every single processor can support integer math, like integer addition, integer subtraction, and integer comparison. Okay, but not a whole lot of platforms can support floating point number calculations in hardware. Okay. You guys have a laptop computer or desktop computer, and those are all fine. Okay, they don't have a problem with doing calculations in double. But your Fitbit, okay, may not be the same. Okay, your cell phone probably cannot do double calculations nearly as fast as your desktop can. So there are situations where we want to avoid the use of double representation, as much as we can, so that we can maintain performance. Yes.
I'm not on the roll.
Uh-oh.
It goes 22 to 26. I wasn't on it either.
22 to 26.
Yeah, this starts at 26 and this ends at 22.
Okay, just write your name on it then. If your name is not on the sheet, it has to do with the printer. For whatever strange reason, the printer does not print correctly. All right, so that means we now have to represent everything using integers. So because we are parsing this string ourselves, in other words, this is now giving to you as a string, as an array of characters. So there would be 1, 2, 3, 4, 5, 6, 7, 8, including the null character. It will take up 8 characters in an array of characters. Okay, is that part okay? Because you have a character for the digit 4, another one for the period, another one for the 5, 6. So we have 1, 2, 3, 4, 5, 6, 7, and then followed by a null terminator, because that is how a C string terminates. So is that okay? That is what you're given with. Okay, now that might be coming in from a file or whatever, but we can assume that we can read the string into an array. Now, if we are parsing it, then we can parse out the 4, 5, 6, and remember where is the position of the decimal point. But we don't have to represent that as 4.56. We just have to say, okay, it's 456 divided by 100 times 10 to the power of 60. Is that okay? So instead of using the decimal point, I just have to remember what power of 10 should I divide from the mantissa that has no decimal point. Is that okay? But that's actually not too bad, because now we can say this in return is really 456 times 10 to the power of 58, because 10 to the power of 60 divided by 100 is 10 to the power of 58. Is that okay? So you do have to remember some of your math, related to exponents and stuff like that. Okay. So now we go okay, so eventually what we want to do is to get rid of the power of 10. We want to get rid of 10 to the power of 58. Or you can say we want to decrease the power of 10 from 58 all the way down to 0. Okay, that's what we want to do. So the first part of this is not too hard to do, because we can just say, oh, this can be rewritten as 4,560 times 10 to the power of 57. Do we have any problem with this? Okay, that's fairly easy to do. And you can use the same method and then go like, oh, I can rewrite this, just add one more zero to the right-hand side of the mantissa, which is definitely no longer normalized, but that's part of the process. Is that okay? The question is, how far can you carry this out? Okay, that's the question. So at some point, we are going to run up to the limit of what is the largest value you can represent using a 64-bit integer. So from our unsigned representation discussion, what is the largest integer that you can represent using 64 bits? You don't have to give me the exact number, but tell me how you calculate it. We got 64 bits. What is the largest unsigned value that we can represent using 64 bits?
64 minus 1.
Yep, 2 to the power of 64 minus 1. Okay. So if you use a calculator, you can find out exactly what it is. But without even using a calculator, I can sort of guesstimate what it is going to look like, okay? So on the side, I look at this, and I go like, this is about 2 to the power of 4 times 2 to the power of 10, and that whole thing to the power of 6. Okay? Well, this is exact equality, okay? Because I'm just moving the power, the exponent of 64 around, because you can see how 4 plus 10 times 6 is 64. Okay? But why do I bother to rewrite it like that? That is because this is now 16 on one side, but the other side I can now have to say approximately. So this is my way of saying approximation, okay? Tilde and then the equal to, because it's no longer a actual equality, but it's close for estimation purposes. So this would be 1, 1, 2, 3, 1, 2, 3, 1, 2, 3, da da da, da da da, 6, right? Yep, 1, 2, 3, 4, 5, 6. Okay, there we go. How do I know that? Because 2 to the power of 10 is 1024, and I say, that's close enough to 1000. Okay, what is 1000? 1000 is 3 zeros in base 10. So since we have 1000 or 1024 to the power of 6, I say, it's close enough to 1000 to the power of 6, and that's why we have 18 zeros. Is that okay? So when you multiply this out, okay, that means it is approximately equaling to 16, and then followed by, guess what? The whole bunch of zeros that we saw earlier. There we go. Is that okay? Now, why is that important? Because I have to find out when I can no longer multiply 10 to the mantissa, because I have to restrict myself to everything should be doable in 64-bit unsigned integer math. Which means if I keep multiplying 10 to the mantissa, at some point that mantissa is going to exceed that amount. So I have to stop before it exceeds the amount that I can represent in 64 bits.
So you can add 14 more zeros?
So we can have, so this would be the 4, the 5 over here, right? So it's 4, 5, 0, 4, 5, 6, and then followed by the rest being 0. So that's 5 times 3 plus 1, 16 zeros. Yep. All right, so I will just go ahead and write that out here because it will be 4, 5, 6, 0, and then we have, this is the second group, third, fourth, fifth, sixth. Because if I multiply this by 10 one more time, it's going to exceed the largest value I can represent.
Right.
Okay? So now the question is, do I still have any leftover power of 10, as a result of that? Well, let's just count, right? So how many zeros have I introduced compared to the row before? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you're right, we introduced 14 additional zeros, which means what can we do to the exponent of 10? Reduce it by 14, so that will make it 10 to the power of, what, 42? I think.
Yeah.
Yes? Okay. And we are now stuck because we can no longer keep using this approach because we don't have quote unquote room to multiply the mantissa by 10 any further. Is that okay? But I can cheat a little bit, okay? So the way I'm going to cheat here is to say, well, we can do something like this, okay? So I'm going to work on this step by step so that you guys can look at the math and go like, yeah, that makes sense. And of course, at the end of the class, we'll start to forget and go like, no, it doesn't make sense. What happened here? Okay. Undo. There we go. Okay, does that make sense? I can just multiply the whole thing by 1? Yeah? Okay. So in this case, I have to kind of do a quick mental math here and figure out, okay, I think we can make it, it's 16 or 8. I think we can make it 16. Okay. Would that be okay? Can I re-express 1 as 16 divided by 16? Okay, cool. And can I move that 16 divided by 16 around just a little bit? In other words, I will do the division by 16 over here, but I will keep the multiplication by 16 to a later point. Would that be okay? Sure, okay. And I look at this and go like, okay, let's figure out, and I would rewrite this as 2 to the power 4. Would that be fine? I mean, 16 is 2 to the power 4. So now I just have to carry out this division here, okay, which I'll do over here. It's 4, 5, 6, and then followed by 15 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And of course, you cannot see that part. I'm going to show you that part here. Okay. And we want to divide that by 16. Okay. So it becomes this amount. Okay. We look at this. Control Shift copy. And then paste it into here. Just copy the rest of the line, and there's no new change here. All right, so we look at this particular value, and of course, we will make it easier to read by chopping these into that. Do you think we have room to multiply by 10 again? I think so. So we can multiply this amount by 10, is it by 100? No, by 10 only. Yeah.
You sure?
You
could fit 100.
If it can do, okay, so if it can divide by 10 by 100, then I did the math wrong. Okay, so let's try the other one. Let's try to divide this by 8, 5, 7, and did I count the zeros correctly? Okay. The zeros are counted correctly.
Oh, you mean divide it by 100?
Yeah, or multiply. What power of 10 can I multiply to this before I run out of room with a 64-bit integer? That's the question. If I multiply by 10, I get 2805 blah 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 blah, which is definitely, okay, 1, 2, 3, 4, 5 groups. So it's definitely less than this. If I multiply this by 100, so I think I should divide this by 8 and not 16. Yeah, because I want to just barely make enough room for a multiplication by 10. I can multiply this by 100 now, which is not just barely, okay? So I did my mental math wrong. It's not that big of a change. All it is my estimate is wrong when I need to only divide this by 8 instead of 16. The approach is still the same. It's just that I chose the wrong power of 2, because depending on what value you're working with, sometimes it's 8 and sometimes it is 16. And the reason is 10 is between 8 and 16. So But I'll tell you exactly the math to get this done. But for the time being, I'm just going to replace all of this with the correct result, which is this number here. You can see it's really just off by 2 digits. Okay. There we go. Okay, so let me chop again. There we go. So if I multiply this number by 10, something doesn't seem right to me. I think I'm off by, I think I know what. I think this number here is off by 1. There's 1 missing 0 here. I think that is the case. So this really is that. That makes more sense. That makes a lot more sense. Right? I was missing 1 0 here. When I copied the number to the calculator to do the calculation, I did not enter the correct number of zeros. Okay, because it kind of makes sense, right? Because if you ignore, these zeros here, 4,500 something divided by 8 should be 500 something, not 57. Okay, so that's just, the order of magnitude was off by 10. Okay, but the idea is still the same. Okay, so it is still the same idea. So now that I have room to multiply by 10 again, the mantissa now has room. Now the next step is to say, we'll just go ahead and multiply this by 10. So now it becomes 5, 7, 0, 0, 0, and what should I put here? 41, because the mantissa is 10 times of what it was. So the exponent has to decrease by 1 if I were to represent the same value. Okay. Is that okay? Is that math working out okay? But did you guys see what I just did? What was the quote-unquote cheat? So that I can keep decreasing the power of 10. I introduce this part here. I say, the mantissa I can no longer multiply the mantissa by 10, because if I did, it would exceed what I can represent in a 64-bit unsigned integer. So what do? I divide it. I divide it by not 10, but a power of 2. But how do I make up for that division by a power of 2? Well, we just have to multiply a power of 2 at the end of everything. So the whole thing becomes a game of moving your power of 10 and transitioning it into a power of 2. That is what we are doing, okay? But there is a division involved. There's a division by 10 involved, a multiplication by 10 involved, and also a division by 2, some power of 2 involved to get this done. Is that okay? So let's do it one more step, just one more revolution, so that we can kind of get a sense of what we are doing here. Okay, so I look at this and say, can I multiply the mantissa, which is now this portion, by 10, and it still does not exceed the maximum number or value that I can represent using a 64-bit number. What do you think? If I multiply this by 10, it would have 5, 7 followed by 18 zeros. That's not going to work, because the most I can do is about 16, actually it's about 18, followed by 18 zeros. So I cannot multiply the mantissa again by 10. What am I going to do? Make room for that multiplication. But how do I make room for that multiplication? Well, it looks like this. So I take this whole thing, okay, remember what we did before, okay, it's going to be exactly the same, but this time I will make it a little bit shorter. So this time I still have to think about, should I use 8 or should I use 16? If I do it by 8, then we have 7, okay. If I do it by, 7, okay, so 8 is fine in this case. So we'll have this again, right? And then what we do is we move around the division by 10 and the multiplication by 10 into different parts. The division by 10 is done to the mantissa. The multiplication by 10 is absorbed by the exponent of 2. So now we rewrite the whole thing like this. Are we doing okay? Yes? Okay. So we have to do the actual calculation, okay? So I'm not even sure whether the other calculator can take all of this stuff here the way it is with all the commas. I'm hoping it would, so we'll see. It doesn't like that. All right, we'll just delete all the commas. There we go. All right, so it gives us this number, and then we'll copy and paste it back. And kind of keep the rest the same, okay, for now. All right, so now we'll chop this, just so that I can double check and make sure that this number is in the correct range of value. Yeah, that looks right to me, right? Because if you multiply this value by 10, it will be 7 comma and then some 18 digits after that, which is fine because we can handle up to 18 followed by 18 zeros. So just having 7 followed by some 18 digits is going to be okay. Is that making any sense? Yes? Okay. So we'll go ahead and do that calculation. Copy and paste. So this time we'll shift everything by 1. In other words, we get rid of, well, actually we don't need to get rid of those. We just have to move the most significant portion a little bit. Okay, the 5 is still here and it becomes 7 and then 1, 2, 5. Actually, there we go. I think so. Is that okay? But since I multiplied this by 10, I'm going to have to decrease the exponent of 10 by 1 to compensate. Because I want the expression, each row should represent the same value. Is that making any sense? So if I make the mantissa 10 times what it was, then I have to decrease the exponent of 10 by 1. Yes?
So you just have to do that 40 more times.
Yep, something like that. But remember, the computer can do that extra 40 times really fast. I cannot do it nearly that fast. Does that make sense? Are we good? So at the end of this process, you can probably kind of imagine that we'll end up with 10 to the power of 0, right? And 2 to the power of some really kind of large value, okay? But nonetheless, we'll end up with a mantissa that can fit into a 64-bit unsigned integer, along with a power of 2 that is non-zero, but it is nonetheless a power of 2. And as long as that power of 2 is less than 1024, we're good, because that is the largest power of 2 we can handle in a double. Okay, but then you will say, wait, Tech, but the mantissa is not normalized. It's okay. Normalization is just a whole bunch of bit shifting. Okay, so we can do all that pretty quickly. Is that okay? All right. So if this is okay, then we have another question, because it looks like we have to carry out a whole lot of multiplication by 10, because if you look at the mantissa, which is here, we have to get it to here, which is a multiplication by 10. So now the question is, can we do a multiplication by 10 really, really fast? But you have to think in base 2, okay? In other words, in base 10, it's super duper easy because we just have to add 1 0 all the way to the right-hand side, right? But what about in base 2? Is this going to be easy to do in base 2? Well, let's think about it. Because I want you guys to start to think about the efficiency of operations. Because there will be times when you're given a very weak processor that is dirt cheap that you have to put into the next generation of Furbies. Okay, no one knows what is a Furby.
Now we know what a Furby is.
Okay,
Nightmare.
they're not gremlins, they're Furbies.
But they're close. Sure. They're close to
They're close, yes. One is organic and the other one is robotic. Yes. But anyway, if you're selling a $20 stuffed animal that is supposed to have some ability to talk and some ability to talk to each other, the Furbies can actually talk to each other, you don't want to put in a processor that is $20, right? Because you're trying to sell the stuffed animal at Walmart for $20. So that means the production cost of the whole thing really should not exceed $2. I'm just kidding. I don't know exactly what is the amount, but let's say it's $2, okay? So that means you have to find a processor that is like dirt cheap, like 50 cents. Okay? Where do you find a processor that is only 50 cents? Well, you can go to DigiKey and look for it, okay? But the problem is a 50 cents processor is not going to have a lot of math capabilities. So if you say, oh, multiplication by 10, we will just use the C subroutine or the C operator to do multiplication by 10, you may find that you don't have enough processing resources to do it. So what do? Well, we look at multiplication by 10, x times 10, and we say, well, what can we do about this? Can we separate this into something like that? Yes. Okay. Then you go like, Tech, you just made it worse. It's now multiplication by 2 and multiplication by 8. This is worse than it was. Wait. Hold on a second here. Right? The less than is a left shift operator, which is basically saying in base 2, you're adding 1 0 to the right-hand side. Okay? Which is the same thing as multiplication by 2. It's a bit shift operation that is multiplication by 2. If you're not convinced, okay, I'm just going to do this part on the whiteboard because it's just a quick one. What is 2 in base 2? Is 1 0. What is 4? 1 0 0 in base 2. So 2 left shift by 1 is just padding 1 0 in base 2. Is that okay? We're shifting in a 0 from the right-hand side. That's what the left shift operator does in C and C++. Okay? What about the 8 then? What do you think? If multiplication by 2 is done by shifting 1 0, what is multiplication by 8? 3. Okay. And bit shift operations are dirt cheap on any processor architecture. Okay? It's much faster than a general purpose multiplication because a general purpose multiplication would involve, even for 8 by 8 multiplication, it would involve 8 separate steps. Okay? And then you have 8 addition and whatnot. This is like easily only 1/4 of the time of a general purpose multiplication. Are we good so far? Okay? So this is the kind of optimization that we are talking about. In other words, we can look at the transition between these two and go like, oh, that is dirt cheap. Because what is involved between these two steps? We have one left shift by 1 and one left shift by 3, and an addition as far as the mantissa is concerned. That is dirt cheap on any processor architecture. But wait, there's one more thing we need to do. We need to change the exponent of 10. That's just a decrement. Also dirt cheap. Is that okay? So we have this dirt cheap operation. Then you go like, but wait, Tech, there are other things that are kind of expensive too because we have this operation here. Okay? So we'll make a transition between the two so that I can identify what needs to happen between these two rows. What about this? We have a division and then we have to adjust, the adjustment of the exponent is done earlier. Okay, but what about the division by 8? What can we do about division by 8? Exactly. If left shifting by 3 is multiplication by 8, what do you think is division by 8? It's right shifting by 3. Okay? Does it make sense? Because left is the opposite of right. Well, that's my right, not yours. And multiplication is the opposite of division. So it does work out that way. Okay? And what do you think of the cost, okay, in terms of processor time of a right shift operation? Dirt cheap. Okay? So we can do all this stuff with a tiny little 8-bit processor. Even an 8-bit processor can do this fairly quickly, okay, even though they're 64-bit numbers. So at the end of all of this, okay, we'll end up with a number, which I do not know what the mantissa would look like, but it would have an exponent of 10 that is a 0, and then an exponent of 2 that is some E2 number. Okay, that is the objective. Once we get it into this representation, this M2, by the way, is going to be, it's guaranteed to be, okay, let me quantify this, okay? This M2 is guaranteed to be between 2 to the power of 63 and 2 to the power of 64 minus 1. And let me just be sure about which part is which part. Does that look like something that you have seen before in your lab? Yep. So with an M2 like this, what does it look like? What do you think this M2 is going to look like? It is greater than or equal to 2 to the power of 63, but it is also guaranteed to be less than or equal to 2 to the power of 64 minus 1. What do you think it's going to look like? What do you think is going to be bit 63 of this mantissa? It's guaranteed to be a 1, right? And it's just followed by a whole bunch of digits, which may or may not be zeros and which can be zeros or ones. We don't know exactly what the other 63 bits are, but we know the most significant bit is a 1. Is that okay? Because throughout this entire process, we kind of made sure that that is the case. Are we good? Well, actually, I lied. It's going to be close to this range, but not exactly. So even this part is not guaranteed. It might be a little bit smaller than that. Is that okay? All right. So now the next consideration is, well, are we going to lose precision? Are we going to introduce error in this whole process? Well, the answer is yes. Okay, we can actually introduce error in this whole process. So we'll go through all the math that we have to do and try to figure out which one can introduce errors. Okay, this step cannot introduce errors because it's multiplication by 10, and because we know for sure that the mantissa has room for another multiplication by 10, that means the result after the multiplication by 10 is exact. Okay, we're going to lose anything. There won't be any errors involved in this process. Okay. What about the other one? What about the other arithmetic operation that we have to do? Which is between these two, there's a division by 8. Division by 8 is an integer division, which means we only keep the integer part of the result of the division. We are going to lose the fractional part. But when you look at these two, it doesn't look like a problem, does it? Right? Because, hey, this is exact. But as you carry out this operation, you will see that these non-zero digits will start to move in this direction, and then at some point that division by 8 is going to introduce errors. Is that okay? So now we actually have to deal with errors because it is inevitable that at some point we will end up with errors. So now the question is, what do we do about that error? Can we characterize that error first? Okay. So what I'll do is I'm going to show you a few calculations, and they're all divisions by 8, okay? And you can tell me what is the amount of error involved in that division, okay? So we'll start with 15 divided by 8, okay? 15 divided by 8, as an integer division, what is it? It's 1, okay? But what is the actual value? The actual is going to be 1 and 7/8, right? What is the error? The error is the difference between the actual and what we have divided by the correct answer, which is 1 and 7/8. That is the error. Is that okay? Is that error, if I were to express this error in percentage, and I just need an estimate of that percentage, what is it? Just give me an approximation. We call 7/8 close to 1, okay? So that means the error is about 1/2, which is 50%. That's a lot of error, okay? So we say that's about, okay, 50%. Not good. We are losing a lot of precision this way, okay? So another division by 8. And this time we have, let's call that, this, okay? What is the correct answer here? Okay, so I have the unfair advantage of being able to copy and paste. Oops, I just missed 1 0. That's how I got rid of the other one. Dang it. There we go. Right?
Yep.
What is the actual? This is the integer. This is the result of integer division. What is the actual? The actual is going to be about the same thing, but add to it 7/8. Nope, there's no error in this case. Okay, fine. We'll make an error here. Okay, so now we have an error. Okay, but the point is still the same. I just did not make the first example actually having an error, but this time now it has an error. Is that okay? So this is the number that is this is what you get when you have integer division, but this is the actual result of the division. So what is the error? It's pretty small, right? So the error is going to be the same amount, which is 7/8, but this time it is divided by a much larger number. This is a much, much larger number here. So this is really small, okay? If I were to quantify it, you can count the number of zeros, right? So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we got 12 zeros, which means the error is about 1E, what was it again? 12? Something like that, which is really small. So what is that telling you? It's telling you that before you divide, it's nice to have the dividend to be as large as you possibly can get it. Is that okay? And how do we make the how do we make the dividend as large as possible?
Get it between 2 to the power of 63.
Yep, exactly. Just make it as large as possible until until another multiplication by 2 is going to exceed what you can represent as a 64-bit number. Is that okay? Cool.
That's why I make the mantissa as big as possible.
Exactly. That is why we want to make the mantissa as large as possible before we divide, to reduce the error. Okay. So now we identify the problem, which is, division can introduce errors. But we also found a solution, which is to make the dividend as large as possible before we divide. Okay? Because it's easy to make up for making that mantissa as large as possible, because we can always adjust the exponent of 2 to compensate for that. Okay? So that means, we can just make the mantissa really large and remember that it's not supposed to be that large by adjusting the exponent in base 2. Are we good so far? Okay. But then there's one more problem. Because when you look at the integer division here, the error is always going in one direction. In other words, the result of the integer division, which is this, okay, is it always less than or always greater than the actual answer? It's always less than, okay? But that becomes a problem. Because in the previous one, if you kind of imagine what we have to do, which is like 40 something repetition of that, division multiplied by 10, division by some power of 2, multiplication by 10, we have to do it 40 times. And every time we do it, we introduce a very small error. But that error is always making it smaller. The answer is always smaller than what it should be. That is called a bias. Okay, when we are doing math calculations, we have a bias. The bias is basically saying, we are always leaning on one side of the error instead of both sides of the error. Is that okay? Is that a good thing or a bad thing? Is biased better, or do you think is unbiased better?
Unbiased.
Unbiased is better because it basically says, well, the error will go in both directions, so they will, for the most part, kind of cancel out each other. As opposed to it's always leaning on one side, so the more calculations you go through, the more iterations you go through, the final answer will become smaller and smaller and smaller and smaller. Okay? So we don't want it to be biased. So now the question is, well, but how do we make it not biased? We want rounding, right? So we want to do rounding after, we want to perform rounding to the division, to the result of a division, okay? But how do we do that? So this is also in the lab, okay? So we look at the round function, okay? We want to round x. So when x is 1.5, we round it to 2. When x is 1.3, we round it to 1. Okay, when x is 1, we round it to exactly 1, right? If x is 1.9, we round it to 2 again. So we want to round it. But how do you express rounding? Well, there are many ways to express rounding. One way to express it is to say, well, we'll take the floor of x plus 0.5. This is one way to do it. Okay, let's check it. Does it make sense, right? So let's take the round of 1. And TAC claims that the round of 1 is the floor of 1.0.5. Does it make sense? 1 plus 0.5 is 1.5. The floor of 1.5 is indeed 1. Okay, maybe it's a fluke. Let's try something else. 1.9, okay? So we want to take the round of 1.9. 1.9 plus 0.5 is 2.4. The floor of 2.4 is 2. Is 2 the rounded version of 1.9? Yep, that works. Let's give it a boundary case, which is 1.5, okay? 1.5 plus 0.5 is 2. The floor of 2 is 2. Okay, so it looks like this works. Yes? But then somebody's going to complain and say, you're being inconsistent with yourself because earlier you said, we want to boil everything down to only integer operations. This adding of a 0.5 basically means it is not an integer math anymore. Right? So how do we fix this? Well, okay, in this very specific case, we are always dividing 8 by a power of 2. Yes? It's either 8 or 16. We haven't seen the case that when we need a 16, but there are cases when we need to divide it by 16. But nonetheless, it is a power of 2. So we'll just use an example of 8, okay? Because eventually what we want to do is to get to the result of some number divided by 8. So you go like, okay, how do we convert all of this into non-floating point calculations? In other words, how do we do all of this in integer math? Okay. Well, let's see what we can do in algebra here. Okay. Can we do something like that? I know this is not easy to see, but if I express it using the usual way, it would be very clear. Because we have x divided by 8 plus 0.5, right? Okay, so I can now say x plus 8 times 0.5 divided by 8. Is that okay? That's what it's expressing. Are we good? Okay. So, and then you just carry out some of the math here. Can we get rid of the 0.5? Can we eliminate the need to represent 0.5? Sure, because that 0.5 is multiplied by 8, which is just 4. Okay? So it becomes the floor of x plus 4 divided by 8. Does it make sense? Can we do all of this using just integer math? Including the floor? Wait, we are taking the floor of an integer division. So that means the floor is not even needed, because once we change that slash into integer division, the floor is automatically applied. Is that okay? And somebody is going to say, but division is long, division is time consuming. What do we do about this? Yep, we just say x plus 4, dirt cheap, the other way around, right shift by 3. Then we are combining the division and the rounding into dirt cheap arithmetic function that a computer can do. Now, how do we know that addition is going to be dirt cheap in terms of time? Because we know about carry look ahead adders. So are we good with this? Sort of? So now we have just talked about the entire thing. We now know the whole process of converting a string, okay, that is expressing a base 10 scientific notation into some mantissa times 2 to some power. Okay, we don't really care what power, because it's just a whole bunch of shifting operations, and we can normalize everything. Is that okay? All right. But wait, this particular scheme only works when we're dealing with something that has a large power of 10 to begin with. Okay? So what do we need to do if we want to go the opposite direction? In other words, what if this is what we're given? Then what do we do? What do you think? Come on, come on, come on. Yes, but how are you going to reverse that operation? Okay, start with the power of 10. So start the thinking process, looking at this and go like, what do we want to do with the negative 60? We want to make it 0, right? So, okay, so let's take a look at the whole process. How do we make it 0? So 4.56 times 10 to the power of negative 60 this time. Okay, first of all, we convert this into 456 times 10 to the power of negative 62, because remember, we want to represent everything using only integers, right? So the 4.56 now is 456. The implicit division by 100 is just by adjusting the exponent of 10 and decrease it by 2. Then we have the quote-unquote implicit division by 100. Is that okay? Okay, so that part is fairly easy to do. But now the question is, I need to do something so that this is now, so that we are decreasing the power of 10. So what can we do to decrease the power of 10? Well, we can divide the mantissa by 10 and then increase the exponent by 1. But that wouldn't be very nice because we have a pretty small number to begin with. If you divide 456 by 10, your error is going to be, 6 over 46 or so. That is not good. So what do we need to do? We want to make this as large as possible first before we do the division by 10. Is that okay? So now it becomes a question of, well, but how big can we make it before we say, okay, you can no longer make this any bigger. So we'll just do it one step at a time, okay? 456, and we'll use the calculator behind this. 456 times 2, okay, is 912. So we'll say, we can write this as 912 times 10 to the power of negative 62. But now we have to make up for that times 2. How do we make up for that times 2? 2 to the power of, no, negative 1. Because we doubled the mantissa, which means somewhere we need to divide it by 2, right? To make up for, because we want to represent the same value. Every single row has to be the same value. If I double this, I better find some other way to take away that doubling. Well, if you introduce a 2 to the power of negative 1, that's the same thing as halving. Is that okay? Cool. I look at 912 and say, well, is it even close to using all 64 bits of a 64-bit number? Nope. Okay, then we keep doubling it. Okay, so we now say, there's got to be a better way to do this. So times 2 to the power of 2, which is 4. You can do it. Okay, so we got 1824. Okay, 1824 times. So you can see that we are not doing a single thing about the exponent of 10. All I'm doing right now is to make the mantissa larger and larger and larger, doubling every single time. Is that okay? So now the question is, how many times do I need to double it until we get to the largest possible mantissa before we run out of room? That's the question. So what do you guys remember some math like that in the labs that we have done? Okay, so there are several ways to do it. Okay, if you're doing it by hand, if you don't understand how to use log and exponent and stuff like that, you can use a spreadsheet. Okay, the spreadsheet will only have up to like 64 items. You just kind of visually scan for it. Let's do it that way first, and then we'll find a better way to do it. Okay. So I'm just going to use LibreOffice Calc. You can use any type of spreadsheet. This just it's just a whole lot. It's just easy to work with. Okay. So we start with 1824, and the exponent that we are dealing with is -2 already. Okay. And we want to compare this to the largest, we want to compare this to 1/2 of the largest integer we can represent in base 2, because if it is at least greater than or equal to that, we need to stop. Does it make sense? Let me say that one more time. We have to compare this number to 1/2 of the largest integer you can represent using 64 bits. Because if the number in column A is greater than or equal to 1/2 of the largest integer you can represent using in 64 bits, you cannot multiply by 2 anymore. Yes? Okay. So that's what column C is going to do, is really just to compare. So all it is comparing is whatever is in column A, and it wants to know whether it is greater than or equal to the power of 2 raised to 64 in this case, and there's actually a -1 involved, but that's good enough. So this cell is just going to be this cell times 2, and this cell is going to be this cell minus 1, which is a compensation of the multiplication by 2 of the other one. And this one is exactly the same as the previous one, so now we can just copy that. And then we take all three and extend it out. It will know it will be terminating, before we get to 64.
Wait,
so
before you do that, shouldn't you want to? Oh wait, never mind. I already did that.
sorry. Okay, so we can see right here that this is the last value. This is, at this point it becomes true. So this is greater than or equal to, oh, I forgot the division by 2, did I? Yep. Okay. So I'll fix that because I really want this to work. It will tell us when we are going to stop. So it's going to be this number divided by 2, because that means we cannot multiply it one more time and expect it to fit in 64 bits. Okay. So basically it just moved up by 1 row, but that's okay. That's okay, because it is telling us that this is when we stop. The exit condition is now true. Okay? Now, when I say exit condition, what do you think I'm implying when you need to do it in a program? A loop, exactly. Or recursion.
No.
Yes. Or recursion.
We're working with not a lot of processor.
Stack space. Yeah. Recursion just needs stack space. Okay. So this tells us that we can keep doing this until we get down to negative 55, and it is currently negative 2. So we have 53 to add to it. Okay, so we basically just adjust this to 1024 times 2 to the power of 53, which is this number here, and Control-Shift copy and paste. Okay, and we still have that stupid 10 to the power of negative 62 here, and it is now 2 to the power of negative 50 what? 53, 55. Okay. Question: are we really still talking about the same value as before? That's the question. Well, we can put it into a spreadsheet or something like that and just do a double check, right? So I'm just going to double check using the spreadsheet because the calculator that I'm using doesn't really do large numbers very well. I mean, it would display in a very stupid way. So I'm just gonna. Nope. Okay. I'm going to copy this equation over here. Okay, first of all, I'm going to convert this into power, because the spreadsheet, I don't think it recognizes the caret symbol to mean power. So I'm going to convert this to power 2, comma, to negative 55. And this is now power 10, negative 60. Oh, yep, it is still negative 62. And that's just a number. Okay, so copy that and paste it here without the equal sign, because I can always introduce the equal sign later on, like here. Okay, there we go. Yay, that worked. It makes me happy that I'm not wrong. But is that okay? Do you guys see how we are preserving the value, but I'm just doing a whole bunch of stuff with the mantissa and the power of 2. But tech is not still doing what I really need to do, because what I really need to do is to turn this negative 62, which is the exponent of 10, into negative 61, right? How do we do that? Well, we use the same approach as last time, right? Times 1. But this time the 1 is expressed as 10 divided by 10. So now we have to say, okay, what are we dividing by 10 and what are we multiplying by 10? The division by 10 is applied to the mantissa. We have just made the mantissa as large as possible. So even though the division is going to have an error, it's going to be minimal. But remember, we also have to do some rounding, right? So what do we need to do to this particular division so that we have rounding built in to that division? What do we need to add to the numerator in order to have a built-in rounding? It's 1/2 of the denominator. So we just have to add 5 to this before we do the division by 10. That's how we do rounding. Okay. What about the division by, so that's division by 10, and we can now say the multiplication by 10, we just make it go here, and then we have no need for this stuff anymore because we have just distributed the multiplication by 10 and the division by 10 throughout different parts of the whole expression. Is that okay? Yes? Okay. So first thing first, we're going to do this division. And we go to the simplistic calculator here. And this is the result. And we go back here. And then we just paste. There we go. What about that power of 10? We can now add 1 to it, right? So we are still taking a power of 10, but it's no longer negative 62, it's negative 61 now. Cool. And the power of 2 is the same, okay? It's 2 to the power of negative 55. Okay, so we look at this mess here, and we say, good. We now have, a power of 10 that is one step closer to 0. What do we do next? Yes?
Why do we add 5?
To do the rounding.
Okay.
So everything here is an integer math. Now you might say, but the powers are not integer math.
But we're not calculating.
But we are not calculating. We are just tracking. All we are doing is tracking the power of 10 and the power of 2. We are not actually computing the power. Is that okay? So there's no calculation on this side other than adding 1 and subtracting. Yep.
Could the adding 5 ever become a problem? Or is it because we made it?
Yes. So what you're saying is true, because what we need to do is to make sure that the comparison in the spreadsheet, okay, if we go back to the spreadsheet here, so this comparison really need to take that plus 5 into consideration. So we need to actually do a minus 5 here. Oops. Yeah, so we need to do a minus 5 here. Let me think. So the plus 5 is applied first, which means it is done last. Huh?
Add 9 to the power.
Add 9 to the power.
No, sorry, minus 11.
Yeah, I think you need this, technically speaking, this minus 5 is needed here because we are adding 5 first before we divide it by 10. And we have to make sure that add 5 plus 5 does not exceed the amount. But that means the plus 5 needs to go inside the parentheses, so that means we have to minus 4 over here instead of minus 1. Is that good? Okay. Yeah, it doesn't change in most cases. Of all the possible cases, like a very, very small would actually trip this logic. But it is still important to catch it because you don't want your space shuttle to not work. Yeah, exactly. But the approach, does everybody see the approach in this particular case? What are we dividing? This time we are dividing by 10. What are we multiplying? Well, we are multiplying by 2 until it becomes so big that we can no longer multiply by 2. So if you look at this number, it is not large enough anymore. So what are we going to do? Make it bigger. Yep, exactly. So each time you divide it by 10, you can probably multiply it by 2 between 3 to 4 times. And that has to do with 10 is between 8 and 16. So depending on the mantissa at this point, with this one, I think you can multiply by 2 exactly 3 times. So this number times 8 would be the last number you can represent using 64 bits. Because if you multiply it by 2 one more time, it's going to be too big. So the next step, okay, I'll do this one last part, which is the next step. The next step is to take a look at this number, Control C, go back to the calculator, Control Shift V, and we say, what happens if I multiply this by 2 to the power of 3? Okay, it becomes this number. That's pretty much as large as it can get, because if I add one more, if I multiply this by 2 one more time, it's going to exceed what we can represent in 64 bits. So now we take this number, Control Shift C, go back to the other side, and paste. So now we have this number. The power of 10 does not change. It's not time to adjust it yet, but the power of 2 is going to change because we have just multiplied the mantissa by 8, which means we have to decrease the power of 2 by 3. That's right. So now it is becoming that. And once again, I have a mantissa now as large as it can be and still fit within 64-bit, which means if I do a division by 10 with rounding at this point, I have just minimized the amount of error. Is that okay? So that's the next step, is to do this part and then repeat the whole process again. Is that okay?
What were we multiplying by 8 again?
You mean multiplying this part by 8? Is to make it as large as possible, because we want the mantissa, which becomes the dividend in our division, we want to make it as large as possible before we perform the division. Because any division is going to introduce error. And in order to minimize the percentage of the error, the larger the dividend, the better.
All right, so multiplying by 8 would be the largest we can get it without going over?
Yes.
Okay.
Yeah, because if you multiply this number, by 2, it's going to exceed what we can represent using 64 bits as an unsigned integer.
Oh, okay.
Yep. So if you guys want to kind of have carried, because we only got like 5 minutes left, that's not really a whole lot of time to start a new topic. So I might as well just kind of use this opportunity to kind of show you what is the next step here. So we just copy and paste. And then what we want to do is to do a +5 and then the whole thing divided by 10. So once again, the +5 first is for rounding purposes. It is always adding 1/2 of what the denominator is. In this case, it is 10. But that division by 10 needs to be made up by increasing the power of 10. So the power of 10 is now going to go from -61 to -60. Yep.
Is there no shift trick like there was for?
Not as easy, but you can. But there's still a shift trick, because if you think about division, okay, long division in base 10, every division involves a multiplication. Every step of a division, every time you figure out the digit of the quotient, it involves a multiplication. So that multiplication can still be sped up because multiplication by 10 can be done fast. So, oh, right. So we need to do this actual calculation. Oh, why doesn't it like it? Unsafe paste. I think it doesn't like the equal symbol, but the equal symbol is not there. Control C, Control Shift V, there we go. Syntax error, because I missed an open paren. There we go. So now we take this, Control Shift C, go back here. I mean, you probably get a general idea of what this is doing. The rest, I can just copy and paste. Okay, so just to test, do you know what we need to do at this point? What is the next step? Go ahead.
Keep multiplying them by 2 until it's less than 2 to the 64.
Yep. So with this one, I think multiplication by 8 is going to work again. So you multiply this by 8, decrease the power by 3, the power of 2 by 3. Then you end up with a mantissa that is once again as large as we can get, and it still fits in 64 bits. Then you do a plus 5 and division by 10 again, and that will give you, that will increase the power of 2, increase the power of 10 by 1, so you're now one step closer again. So you can see the process is almost exactly the reverse of the other one, okay? Except what we're dividing is 10, and what we are multiplying is a power of 2. Is that okay? Are we good? All right. So if I were to ask you not to do this by hand, because it would be kind of crazy to do this kind of number by hand, can you write a program to do it? Yes, okay. I see a lot of nods because that's your next homework assignment. All right, I'll see you guys in the lab, and we'll get started with this one. It's basically a homework assignment, and I'll give you some extra instructions in the lab as well, because you'll need some extra instruction to get started with code blocks in this case. So I'll see you guys in about 10 minutes, and give me a moment here to, actually I can do all of that at the lab, so we'll just go to the lab.